Here I introduce what is called L1 space. So this is something which is denoted by this symbol, and by definition this is the collection of all those classes of equivalent functions, measurable equivalent functions, such that, and I will explain what this symbol means. This symbol, when we write something like this, norm 1 of the equivalence class is finite. This, we interpret this writing as this, that the absolute value of the representative of one representative from this class is Lebesgue integrable. Lebesgue integrable in the sense we introduced earlier, and this symbol represents the integral of the absolute value of this representative. There is a typo here. It here means to be a class. This definition is correct, meaning that if I have another representative in my equivalence class, if I have another representative in my equivalence class, then the absolute value of this another representative will also be integrable, Lebesgue integrable, and in fact they will deliver the same integrals. This follows from the fact that if you alter a function on a set of measure 0, the Lebesgue integral, the way it was defined, will not change. I'm not going to prove this statement. It's rather a routine statement which almost directly follows from the definition, but still it is a statement which in general requires a proof. So this definition of the norm, L1 norm, we will call this symbol L1 norm, although we're not going to put any meaning in that. I mean, people who studied Banach spaces, they will probably see more meaning in this, but I will use this just simply as a term which will refer to this symbol. Now, the basic properties of this space, L1 space and L1 norm, I all collected them in this lemma, and here it is. The class of measurable functions is integrable or belongs to this L1 space if and only if the class associated with the absolute value of the representative belongs to this space L1. Something we actually also stated in terms of for the simple functions, but given the definition of the Lebesgue integrability is based on the integrability of simple functions, this result can be easily derived from similar result for simple functions. Now, linearity property sounds like this. If I have two classes from L1 space, then the linear combination of those two classes will also be from L1 space, and we have a version of triangle inequality for the L1 norm. Property C says if I have a class f from L1 space, and if I have another function g which is controlled in absolute value, which is controlled by one single representative from this class, no matter which one, then the class associated with function g will also be in L1, and we have the following relation between the integrals and norms. Now, we also need the following space, which I will call L infinity space, and that will be, look at this, it will be the collection of all those classes of measurable functions such that there is a representative in the class, one is enough, such that this representative is a bounded function. For such classes of measurable functions, which from L infinity space, in fact, this space is called L infinity space. Let me just put here the name. For every class from the L infinity space, we can introduce L infinity norm, and that's what we do. That's how we do it. We take the infimum across all representatives from the class, and we compute the max norm of every representative, and the infimum of these max norms will be the value for the infinity norm of my class. Given this new norm, again, this term norm doesn't mean anything. but simply just used for the reference purposes only, L infinity norm. We have a property number, property D, which says that the L infinity space is a subspace in, or actually, normally subspace, not really a good reference to this statement. L infinity is continuously embedded into L1, and when they say that this continuously embedded is explained by this inequality. It means that for every class, I'm missing the term class here. For every class from L infinity, the class will also be in L1, and the norm of this class in L1 is controlled by the right hand side like this. Of course, this is only true when your measure space is finite, because you need this factor to be finite. And finally, part E, for those who knows a little bit of Banach spaces, part E is nothing else but the property of completeness. It says this: if I have a sequence of elements, sequence of clauses in L1, such that it is Cauchy, such that this limit is 0 when indices n and k, they go to infinity independently. That's exactly says to us that the sequence Fn is a Cauchy sequence. Then there is a limit point in my L1 space. There's a limit point in my L1 space. This is a property of completeness. Altogether, these 5 properties, they say that L infinity is the Banach space. But you don't have to use this language, just this explicit mentioning of these properties will also do.